On behalf of yeah, on behalf of Society of Energy Engineers and Managers, Maharashtra Chapter, I welcome you all for this webinar. What we have planned is every month on one of the Saturdays in the evening, we will like to have webinar on the current topics. Today's topic, as you know, is deep dive in implementation of rooftop solar and its effect on power factor by Mr. Sudhir Budhay, who is also energy manager. So at the outset, I would like to thanks ECE India Limited, a leading manufacturer of solar panel, for sponsoring this video link. Thank you, sir. And now I would also like to tell you about Mr. Sudhir Budhay. He is independent solar power project consultant and mentor, trained resource online or offline for technical and regulatory matters. And if you see his experience is more than 45 years. So such an experienced person is there with you, and dedicated solar power industry professional. But he is having expertise in marketing, project implementation, regulatory affairs, and business development. A versatile personality is there with us. He has a proven track record in pioneering floating solar projects. So he is the first one in India to have the solar floating panels, influencing the energy policies and providing technical insights as a guest speaker offline and online. He is a guest speaker, as I told you also. He is the founder, director, and CEO of the Business Algorithm Private Limited, which received prestigious awards like the IDG Premier 100 Award, the CRN Award, and the most coveted, the DQ Gold Award for the fourth successive year. Right? Then his professional skills include team management, DPR and tender drafting, consultation for the solar projects, guest lecturer and trainer, energy laws in India, and energy manager. He is also a member of the many societies like SECI, SEAM, VC, MDWA, and AREA. He is also an energy manager and also energy laws in India certified by the DGEF. The professional experience includes he worked as a works manager for 8 years for manufacturing control panels and understanding electrical contract for electrification. Now you may think that he is an electrical engineer, but I would like to correct you. He is basically a mechanical guy. And see a mechanical person, how much he can do in electrical engineering. Probably I may be unable to do it. I am basically electrical engineer. He is the founder, director, and CEO of the Business Algorithm, I told you, which was founded in 1988, diversified in solar business from 2012. And during his tenure, he commercially implemented the first floating project. That's the most important thing. The first floating project in India in 2016 at Reliance at Butibori near Nagpur, and also signed MOU with Gujarat Energy Research and Management Institute, Gujarat, for developing floating solar projects and solar roads. Then, as I said, that he delivers the guest lectures at the very renowned institutes like VNIT, RKNAC, then at Pune, Government College of Engineering, at so many places he delivers. One more important thing which I would like to tell you about him is about the PIL which he has filed. Why he did that? It is because they restricted the need of grid regulation for Maharashtra in 2012, and he filed a PIL with MERC in 2013, case on 86 of 2013. Those who are interested in details, they can go to this case of 86 on 2013 for networking metering regulations. See how much his public interest is, how much he is socially aware, and he wants to do some social things. He was a member of Net Metering Committee of MERC also. He is actively involved in recent solar related regulations in Maharashtra and a few more PIL like cancellation grid support charge. This is case 176/MP/2023, Then statement of reasons and improvements for grid interactive rooftop notifications 2023 and green energy open access 2023. This is also case 231/MP/2023. Then extension of virtual net metering, case number 226/MP/2023, etc., filed with MERC, and they are all under progress. I think all of you know what the PIL means, right? It's the public interest litigation. There is nothing he is going to gain personally. So he's fighting for all of us in the court of law. And that Biolco company, which I said that he was a founder, he sold that company in 21. And he says that he is retired, but I'm doubtful about it. He's retired. He's such an active person that I don't think he will retire ever. He is working specially as an independent consultant for solar power projects, mentor, and resource person for technical and regulatory training online and offline. He is based at Nagpur. And as a person, he's a good friend of mine. So once you get a friendship with him, it will be a lifelong friendship. So he's such a nice guy. He's with us. So I welcome you, Mr. Sudhir Budhay, for this webinar.
Thank you,
and
sir.
Once again, I would like to thank ECE India Limited, the leading manufacturing solar panel, for sponsoring this video link. And now it is all over to you, Mr. Sudhir.
Thank you, sir. Thank you very much. Thanks for the good words that you have said about me. Good evening, friends. Thanks for joining this webinar. I would like to thank Society of Energy Engineers and Managers, especially and Dr. Khedkar, who himself is an electrical expert, ex-Vice Chancellor of Amravati University, and a retired HOD at VNIT. It's a pleasure to present this topic in his presence. Now, generally, I start with my presentation with a disclaimer that whatever I'm going to present today is true to my belief and understanding of the subject. However, you are all requested to cross-check the same and modify it to meet your specific requirements of your state, category of your consumer, and site requirements also. So I'll be presenting a topic which has become critically important for our industrial landscape. Today, topic addresses technical issues that some of you might have already encountered, a mysterious drop of power factor when we install solar rooftop in industry. This is just not a technical or academic session. It's a real world problem affecting our plant performance and electricity bills. So today we shall cover the change in APFC panel behavior with the injection of solar power in the consumer's network. Then we'll take some examples from the industry. kVAH billing started long back for ST consumers almost 5-6 years back. And now they are capable of handling, they are all tuned to it. They have already installed required power factor controllers and even mitigation of harmonics. So they are through, they have technical manpower. So we don't have to bother much about them. Now the question in Maharashtra, since kVAH billing started from 1st July 2025, even consumers about 20 kilowatt in CNI segment, I'm talking about CNI, commercial and industrial segment, which are typically hospitals, hotels, restaurants, showrooms, workshops, mid-sized offices, all these category of consumers, they mostly have single-phase loads. Now, even though their contractor has perfectly balanced the loading per phase, but he has no control on the usage pattern. So based on the usage per phase, usage of various load combinations of various on per phase, and the reactive power requirement per phase, it is causing a problem in network. Handling power factor near to 0.999 is a challenge. And even harmonics, in case of few LT consumers, is going to be a big issue and we should be prepared to handle that now. We shall cover these cases, a few sample cases, and discuss mitigation strategies. We shall also quickly look at the grid codes and future considerations of power quality so that we are smart grid ready. So let's start. Let me first paint a broader picture of RE power in India. India's solar capacity has grown exponentially. Rooftops are significant contributors to the solar power generation. Benefits are very clear. 30 to 60% reduction in electricity bill, government incentives, and environmental benefits, of course. However, what we often discover after installation of solar, even a carefully tuned APFC, which was perfectly working fine before installation, starts behaving erratically. When power factor degrades, it affects grid stability, which in turn impacts power plant power quality also. This problem is more intense in case of LT consumers because if you see, all ST consumers mostly have three-phase loads and mostly all the phases are evenly balanced. Even if they have few single-phase loads, the percentage of that contribution of single-phase load in the overall loading of balance loading is very negligible and they can manage with three-phase capacitors and three-phase APFCs. The problem is more intense with LT consumers with unbalanced load due to KVH billing which has started in Maharashtra. Few trade bodies are opposing this decision, but there is no point in blaming government regulations. I personally feel they are correct. To explain my point, just give me 5 minutes. I'll quickly take you through the history of how power sector evolved in India. So, uh, India got independence in 47. Elect, even before the constitution was ruled out, energy was a sector of high priority and the Electricity Act 1948 was released even before the constitution. It had two components, central and state, and all state were given monopoly and they were given a task to form a electricity board, state electricity board, which was responsible for generation, transmission, and distribution. Now, need of the time, this decision was correct because in 1948, the need was spreading the distribution network. They wanted the, each district, each taluka, each sub-taluka place, even villages must be electrified as quickly as possible. Of course, it was a political move also because that's a vote bank. So fine. I mean, as long as people are benefited, it's good. So state were investing in network building. In the meantime, what happened? And this process continued. And let me tell you, all the states did a fantastic job in next 20-25 years because every year they had increased ARR, annual revenue requirements for spreading network in their state. Government was funding, they were pushing funds, and the network was getting spreaded over to the internal part of the country also. And that point we must appreciate that all states did excellent job in spreading electricity network. Okay, fine. In the meantime, what happened in 1983? There was a Geneva Convention. It's actually a workshop which was focused on energy conservation and reduction of carbon footprint. That was the first agenda. And second, in order to achieve reduction in carbon footprint, that means reduction in thermal power, the use of wind and solar or alternative resources is was suggested, and India was part of that. Now, this process is going on. India had two problems. So they had to manage the pie in the energy entire country's pie. of energy requirement, they had to keep increasing the renewable energy contribution. Now, somewhere around 85, 90s, uh, the central government was going through election, and the top leaders used to go on rallies and meet various people, and they found that people are still not happy. Even after spending so much of money spreading this network, people were really not very happy because network was there, electricity was not there. There was a blackout. In the sense, the shutdown used to be 12 hours, 8 hours, 15 hours, 18 hours, that kind of a thing, and people were not happy. So they immediately called meeting of all electricity boards. And they said, but what is the problem? Why are you not giving the electricity? They said that we have spreaded the network so fast and so to distinct locations, different locations, that the demand has gone up. Since the demand has gone up, we are not in a position to cope up with generation. They said, okay, go ahead and increase the generation. They said, no, sir, sorry, we have no funds. Even central government was running short of funds. So there was a need. One, generation of electricity, additional electricity was an urgent need that time. See how the policies get evolved and you have to forcibly take certain decisions. So government had first thing they had their first priority was to boost up the power generation. Second, the Geneva Convention proper pressure that was mounting up on India to increase the renewable energy contribution in the entire pie of energy in India, energy consumption in India. So debates were going on, and if you have to encourage generation from private investments, then first need was to amend the Electricity Act 1948. Because of that act, they had all the states had a monopoly. So there was a need to amend the act, and a lot of debate happened, and these people had a lot of meetings and things like this. And finally, Electricity Act 2003 was rolled out, and which is the current act applicable to all of us. It had three major components. First was generation was delicensed. Second, all the state electricity boards were trifurcated. It was converted into generation, transmission, and distribution companies. And thirdly, open access was introduced. Now, suppose since the generation is delicensed, suppose say one company, say Tata wants to come up with 50 megawatt plant at one location. There is a need to transmit this power to some other location. So open access automatically came into picture. Now, out of these three, generation, transmission, and distribution, generation is totally delicensed except for nuclear power and hydropower. Hydro below 25 megawatt is under state control, about 25 megawatt central government. But anyway, these are large value projects. We are not bothered about that. By and large, for us, generation is delicensed, irrespective of whatever sources you use. Okay. But transmission and distribution was still under license regime. Why? The logic behind it is why duplicate the network? Why duplicate the infrastructure? Suppose there is a highway between Delhi and Bombay. Why have parallel highway? So why not pay toll and use the same highway? So same logic was applied here. So through open access, the generator used to pay some wheeling charges, transmission charges, and they started using the same network. Now, since transmission and distribution was under monopoly situation, license regime, there was a need to control their activity. And so, for the benefit of consumers, state regulatory commissions were formed. So each state has their own state regulatory commissions. So that's how Electricity Act 2003 started, and slowly after implementation of this act, the generation started getting geared up. All of you must be remembering that somewhere around 2004, 2005, we were all running to buy normal inverters like Microtech, Luminous, and n number of inverters were there. They did a very good business during that time because of shutdown, because power supply was under problem. Slowly, this situation started improving, and but the problem of RE integration still remained till JNNSM, Jawaharlal Nehru National Solar Mission, which was launched specifically on 11th of January, was launched. It had a simple target of initial target, modest target of 20 gigawatt by 2022, which was revised to 100 gigawatt up to in 2015 by Honorable Prime Minister Narendra Modi ji with 40% contribution from rooftop segment. So focus was to increase the penetration of solar power. Now you will all have a problem when a general question. Okay, when we have option of wind and solar, why focus on solar? See, first thing is wind. Our country is not very much suitable for wind power generation. The viable locations are only across the coastal area and few points in the country. You go to MNRE website, you have the ready-made charts available where the winds are feasible and not. Whereas solar, our country is very well placed. We are very near to equator. Earth is tilted by 23 degrees. So equator plus 23 and equator minus 23. This complete belt of plus 23 and minus 23 across the globe is very much favorable for solar power generation, and we are blessed with solar power. Number two, if you think of wind turbine, technology is high, investments are high, and the power generated is also high, phenomenally. 1.5 megawatt, 2 megawatt, 2.5 megawatt turbines you are installing. What will you do with this kind of a power? So it was out of reach for common man or common industries also for normal requirements. Whereas solar, if you take it's modular, like from 1 kilowatt onwards, you can configure your system to individual consumers' need. Technology is simpler, the cost is less, investments are viable. That's how the solar got momentum in India. So this is precisely what I wanted to tell you. Why we are here to think on the RE integration problems with the grid. Now, since the penetration is increasing, the problems will keep on increasing, and that's why we are here. Now, since all of you are energy managers, I will not waste your time on uh, explaining everything. See, you know this theory. Let me take the laser pointer. Okay, so you know real power, reactive power, apparent power, things like this. Anyway, now as per the regulation, people are built on kVAH basis. So power factor is important. They are built on apparent power, not on real power. So calculation has to be done by DISCOM. And let us see how first to attack this problem. Let us see how DISCOM does the calculation, and we will go one step ahead and see how they get input. So the input will be definitely energy meter. So let's focus on the energy meter also. So I have taken an example of a very popular energy meter of Secure Premier 300. Now, if you see, this is a data sheet. Let us see what parameters it has, what are the output from the energy meter. So based on that, we can definitely focus our studies. So active energy, it gives you measurement for active energy, reactive energy, and also gives a lot of it has got demand registers, 8 demand register, TOD is programmable, it has backup for 90 days data and things like this. Okay, let us focus on our subject. It is giving active energy as well as reactive energy, whether leading or lagging. Okay. Now, apparent energy has to be calculated, and even the catalog says it is calculated from active and reactive components. Now, coming to DISCOM uses this formula, distribution companies, for calculation of power factor. It is very simple, total real power divided by under root of real power square plus sum of leading and lagging power factor square. So that's how they calculate the power factor. Based on the power factor, your energy, kWh, real energy is converted into apparent energy, and you are billed on apparent energy basis. Now, our target as an energy manager is to see that the bill is minimum for our customer. So our target is to see that the reactive power consumption is minimum, and how do we achieve it? So obviously by putting capacitors, I don't have to tell you, these are mostly three-phase capacitors of various size depending on various loads. You keep on switching using APFC panel, okay, blah, 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 that all of you are aware of it. Okay, so let's jump to the placement of cities. They are generally located, or it has to be located between the utility meter and distribution board so that it is measuring the entire current drawn, and the ratios will be X by 5 depending on the whole current. You can design this ratio accuracy class 1% or even better 0.5. VA burden we can calculate. It measures the actual grid flow current and district and import-export parameters also. So let's take a simple example of industry with 5 megawatt connected power and 2 megawatt solar rooftop. Now there are two methods we can see. One is when the solar power is injected directly to the load bus, to LT bus. We have seen that in this case, the power factor drops substantially, and it's not a good sign. But when you connect it to along with the distribution panel or distribution, discom power, then the power factor remains almost the level where they actually wanted to keep it. So first scenario is direct injection into load bus, and second is along with the discom power. So let's first see, in case you are a LT consumer, then we'll have transformer, then meter, and then the LT bus will be there where various loads will be connected. We'll also have some capacitor, fixed capacitors put, or maybe APFC or combination of both. And if you are a ST, then probably meter will be before transformer. Okay, this is a normal scenario. Now, when you want to install solar, the solar integrator will come and he inspects the sites and he says, okay, sir, you have one breaker, 800 amps, 1000 amps, whatever, it's free, extra. I can use this. You can save on the money. So we will install and inject power here. So what he does, he comes, installs panels, installs the inverter and meter and start injecting power. Now by default, each solar inverter is programmed for unity power factor. That means it is only giving real power. It is not giving power for reactive compensation. So what happens? You are injecting power, your load runs. So suppose the current drawn by entire load is say X ampere. You are generating and injecting Y ampere. So I will draw X minus Y from discom. Okay. But what happens? My CTs are here. They cannot sense the total X component. What CTs are sensing is X minus Y. And accordingly, they will fire the capacitors. So that is precisely why capacitor or APFC starts misbehaving. As against that, instead of connecting it here, I can, if I connect it along with the distribution power, then my load is X ampere, generating Y. I am drawing X minus Y. So total power seen by APFC will be X minus Y plus Y. So plus and minus Y gets nullified, and whatever X is being drawn is seen by APFC, and accordingly it fires the trigger for appropriate number of capacitors. So that's precisely what happens with large consumers. So just see whether with solar or with solar in night time. Suppose my demand is 1000 kilowatt. I'm taking power throughout night without any solar power injection from the distribution company or grid supply. So thereby, suppose my power factor is zero point 0.8 lagging, then I'll require 328 kVR to compensate that. But what happens during daytime? Daytime, I start injecting real power into the system. Now I'm injecting 400 kilowatt from solar and 600 I'm drawing from grid. So as a result, my CT senses only the 600 kilowatt load and activates only 197 kVR. So if you go on a power triangle, we can easily see the difference. This is the scene in night or without any solar. The moment you have daytime coming at morning 8 o'clock, solar starts, then real power starts getting into the circuit. But it's not like a generator. You start and suddenly 400 kilowatt getting into your network. No, it will start at say 7:30, 8 o'clock. It will till 12 o'clock. It will slowly get in. It will slowly keep increasing, thereby shifting this particular line from this to this slowly over 4 hours or 4.5 hours. Reverse happens when 12 o'clock onwards till say 4:30 or 5 o'clock, reverse starts happening. This line starts shifting towards this side. That means there is a gradual shifting of my current requirement from grid, and accordingly my compensation changes. So to summarize, what ideally we are doing is this is your power input from DISCOM, this is your breaker, and these are your CTs, maybe for metering, maybe for APFC or whatever. This is the point where I was trying to tell you that we must inject solar power at this particular point. Okay. Now this is very well taken care by most of you, and this is no more a problem because even as we discussed, for large consumers, a slight imbalance in the load really doesn't matter much, and they can I mean that kind of a deviation in reactive power requirement, compensation requirement can be handled by APFC. Now, talking about a solar installation. Now, for that, we'll have to look at the logic how APFC relay takes this. So it starts the operation, measures phase current, measures voltages, and calculates phase power, calculates total power, calculates the requirement of power factor, and accordingly checks whether power factor is within the range or not. If not, then calculate required KVR, select capacitor bank, switch on selected banks, and continue. So this process continues till the steady state is achieved. If it is yes, then it maintains the power factor. That's how the logic in any uh, APFC relay works. Now, comes the question how a unbalanced load, typically again with solar power injection, will behave. So, as I said, 20 kilowatt and above. That means these are all small shops. They are medium-sized offices, maybe showrooms, maybe restaurants, maybe hotels, hospitals. All these are 20 kilowatt and above LT consumers. Now, as we discussed in the first earlier case, it is quite possible that your contractor has done a very good job, but because of the usage pattern switching on and off, your current requirement per phase is differing, and so is the reactive power requirement differing from time to time. So let's take an extreme example. Say the current in R phase is 12 amperes, Y is 24 amperes, V is 45 amperes. Extreme example. Okay. So let's plot it, see a chart. Current is 12, my power is 2.21, then Y phase is 4.42 and B phase is 8.28. What happens to billing? We have seen in the first initial part that energy meter takes a algebraic sum of all three phases. So it will take compute and compute a demand of 14.9, and Discom will happily bill at 14.9. They are happy. They have nothing to lose. Coming to reactive power compensations. Reactive power compensation required in R phase is only 1.66, Y is only 3.31, and B is 6.21. Now, as we have seen in the logic flow chart of APFC panel, capacitor will try and compensate the maximum. That means 6.21 kVAR. The three-phase APFC will try and compensate 6.21 kVAR. Now it will switch on 5, or if it is fine-tuned kind of a APFC, maybe they will have one kVAR as one step also. It will switch on 6 kVAR. Fine. So what happens as a result? Our phase is overcompensated. There is actually no capacitor required. It is going in an export mode. We are exporting reactive power. Same is the case with Y phase. No capacitors are needed for this phase, and B phase is happy. It's fairly okay. So even if you get, this was a steady state example of 12, 24, 45 amperes. Even if you allow a deviation of 10% plus minus per phase, even if you take 96 time blocks in a of interval of 15 minutes, how the energy is stored and calculated. And if you plot a graph, this is actually a graph plotted on 96 intervals. The yellow line is showing the solar power injection, whereas the red line is actually the net power drawn from DISCOM. So here if you see up to 8 o'clock or quarter to 8, the steady power demand is there. After that, it starts reducing, and till 11:30 or quarter to 12, it starts exporting. It starts exporting power to grid till 12:30 or whatever, depending on your capacity and size and location of your installation. And again, the demand on grid will start increasing. So this is precisely what I was trying to draw your attention to. When you are injecting solar power in unbalanced load, your KVR requirement per phase is different, and achieving 0.999 resultant power factor in order to have minimum bill and minimum problems in the grid is very tough in single phase, in case of three phase consumer about 20 kilowatt with most of the single phase loads. Okay. So what do we do? Actually, solution is very simple. You go for static var generator and your problem will be addressed. But these are all LT consumers. Remember, if you tell them the cost of static var generator, he'll say, "Ki boss, jane do. We'll, instead of investing this money, we'll keep on paying this in installment every month. Whatever extra we are paying, we'll be happy." But we are engineers. We are energy managers. So we need to address this problem. So what is suggested? What is ideal? Ideal is we have a APFC where we have three-phase capacitors also, and we have single-phase capacitors, each for three different phases. So ideally, whichever is the lowest value by calculation by from the relay, the three-phase capacitor first gets on, whether 3 kVR, 5 kVR, 10 kVR, 15 kVR, whatever. And whatever is the extra compensation required for that particular phase, Y phase, B phase, whatever, is compensated by a particular single phase bank. So requirement dedicated to each phase for single phase capacitors, and then 4 or 8 stages for three phase capacitors, depending on the combination. So what is the recommendation? The recommendation here is, well, first, as I said, you go for static var generator, finish, no problem. Or you deploy a instrument, APFC. We are talking of 40 kVA kW connected load. We are talking of 30 kW, 25 kW connected load, and we need to have all the three phases balanced now. So bank size, the capacitor bank size will reduce to 0.25, 0.5, 1, 1.25 to 2.5. This kind of a small steps will be required to have a fine tuning to 0.999 kind of a result. So what we go ahead, when we want to select a relay, we have 3, 4 options in the market. One is we can go for linear logic, which is 1:1:1. So I have similar capacitor place 5 kVR, 5 kVR, 5 kVR, 5 kVR. This is example. So you keep switching on in the same linear fashion. Second is exponential steps, binary 1, 2, 1:2, as to 4, as to 8. So we put capacitors 5, 10, 20, 40 kVR. So you use this, or you can go for hybrid where you need to program and tell the relay that stage 1 I have connecting 5 kVR, stage 2 I am connecting 7 kVR, like this. So you do programming, but there are certain smart hybrid relays also available today where they are smart enough to compute. When you get into programming mode, they will compute themselves. They will first discharge the capacitor. Then, based on the charging current, they will calculate and do self configuration automatically. And there are smart hybrid relays with 4 stages for single phase, each phase, and 4 or 8 stages for three-phase capacitors also. Generally, we'll keep the response time as 10 to 30 seconds, typically 20 seconds, in order to avoid hunting. So that's how we come to a conclusion that these kind of products are available, already available in market. See, gone are the days where everything is tailor-made. Even today, whatever shirt we wear, they are ready-made. There was a time when we used to go to tailor and get it tailored to our requirements. Same was the case with APFC. Now gone are the days. Even for LT consumers, 10 kilowatt, 20 kilowatt, 30, 10 kVR, 20 kVR, 30, 40, 50 kVR models are available for three-phase load, for unbalanced load, for even with harmonics control also. The models are ample models are available in market. Just plug and start. That's the kind of scenario we are here today in India. Now, let's go ahead with grid code compliances. Now, Central Electricity Authority has certain regulations where we have to follow grid code, and power factor range is 0.95 leading to 0.95 lagging. Then voltage regulation is plus minus 6% at the point of connection. Then harmonics should be less than 5% for voltage and less than 8% for current. Now, if you are specifically, since we are talking specifically about solar, the anti-islanding protection has to work in half a second. As soon as the grid codes are not made, whether the frequency range is out of range, voltage is out of range, the inverter, solar inverter has to trip within half a second. That's how we are targeting as per CEA, Central Electricity Authority grid codes. Now, let's, since we have touched the harmonics part also, though this is not very prominent today in three-phase consumers LT category, it's not that prominent today, but it's going to be a talk of town tomorrow. And that too with a solar integration. Now, what happens when you install solar? You are putting a switching device by design itself. What I mean is, when you install solar, the solar inverter itself will generate 5th, 7th, and 11th harmonics. Now, 11th harmonics, let's ignore 11th harmonics, the effects are not so high. But if you consider 5th and 7th harmonics, the dark line, dark red line, is the resultant of 5th and 7th harmonics, which is introduced in the system by solar itself. And the situation becomes complex, or because if there are certain capacitors, fixed capacitors or APFC, installed in the installation where solar is getting installed in such a premises, then it can form a resonance condition, in the sense it will create a resonance condition if the impedance equals to system's inductive impedance. So the calculation formula is very simple. Frequency of resolution will be 1 by 2 by under root LC. So for this, what we suggest is, to mitigate this problem, this should have detuned reactor up to 6 to 7% of the harmonics. And plus, if the problem is complex, you can have active harmonic filter also. So let's take a quick example on of a harmonic kind of a situation. So let me make it little loud, like what we saw in unbalanced case, like 12 to 45 ampere kind of a variation. Similarly, let me take an extreme case in harmonics, just for the sake of demonstration. Let me take a data center which is prone to this kind of harmonics, plus we are adding solar. Now suppose there are 100 computers, 100 monitors. They had 300 lights, lighting fixtures, 50 fans, and some few ACs running. Plus, they had APFC, because the the air conditioning load is there. Now, the bill was very high, so management decided to change all the lighting fixtures with LED and all fans with BLDC. Bill reduced a bit. What got added for this establishment was a harmonic. Solar installed harmonics. You have added LED, you have added BLDC fans. Now you are adding harmonics into the system, and they were searching what is the reason why my monitors are failing, why my devices are failing so frequently. Reason, they were trying to see the earthing, ye badal do, wo kar do, SPD laga do. The real solution was in controlling harmonics. And to mitigate harmonics, first solution, definitely, if you want to reduce by 95%, is active harmonic filter. Cost is very high, but it can handle multiple loads, it can handle variable loads. Second is option is relatively low cost, which is passive harmonic filters. Passive harmonic filters will block up to 60 to 80%. We can go in for hybrid combination also. Or as I said, we can go in for APFC with detuned reactors, which will solve up to 50 to 70% of the harmonic problem. So this is how we have to probably address the problems of future as regards to LT consumers, and that too with solar integration in coming future. Now let's talk of protection systems. You are all energy engineers, so I need not repeat it for you, but there are some solar participants also in this seminar. So let me give them a brief that overcurrent protection has to be set at 1.125% of the rated current voltage, plus minus 10%. All relay settings must be plus minus 10%. Earth fault should be 30% of the rated current. So these are the and reverse power protection in case they are not going in for net metering or net billing kind of arrangement. So these are the requirements for grid protection. Then talking about the future technologies, as we said that we should be ready for future technologies, smart grid integration, battery storage integration. We should be ready for predictive artificial intelligence in the load management, smart grid management with different algorithms for predictive PF controls and machine learning optimization, and even, as I said, regulatory evolutions depending on the need of the day. Regulations will keep on changing, so we need to adapt to that also. And even advanced power electronics. Now, silicon carbide and gallium nitride are the semiconductor materials which are they are preferred rather than the traditional silicon. Basically because of higher efficiency, faster switching speeds, and improved performance in converting DC to AC power. These are basically wide band gap materials. They are smaller, lighter, and very robust power systems. Silicon carbide is often preferred for high power, high voltage applications, whereas gallium nitride is ideal for high frequency and lower power devices due to its free electron mobility and switching speeds. So these are the uh, technologies which we have to face tomorrow, and we should be ready right from day one, right from today itself. Coming to best practices, this is basically a summary of what we discussed in last 1 hour. It is best in the design phase itself. You inject power immediately along before the cities along with the grid. Then in case of unbalanced load, try and go for three phase plus single phase corrections. For harmonics, you can go in for detuned capacitors. Then all this you are all aware. I will not waste your time on this. We are approaching to our closing time, so I'll quickly move ahead. Now coming to technical references, Indian standards. These are all IS standards which you can refer. Then international standards, IEC, IEEE, and IC standards. These are the normal standards which all of us we have to follow. Coming to technical literatures, CA Central City Authority, technical literatures and technical standards are available. Then Bureau of Energy Efficiency, हमारा जो Bible है, energy managers का, the guidelines by BEE are most important for us. And for the solar people, guidelines, technical guidelines and technical reports by Ministry of Energy, New and Energy, Renewable Energy Department is their Bible. So they will go by their standards. So with this, I am about to finish my presentation. But before I conclude, I would like to say that energy management profession stands at a pivotal moment in India today. The challenges we face are from grid modernization and RE integration. This does not only require technical expertise, but a collaborative leadership that brings together diverse perspective and innovative solutions. Our society, Society of Energy Managers, has tremendous potential to shape the energy landscape of tomorrow for India. And I believe that we need leaders who can bridge the gap between technical excellence and practical implementation. Having had the privilege of leading organizations both in IT as well as solar integration, I have witnessed that firsthand, as a first-hand entrepreneur, how professional societies can transform industries when they are in evolving stage and have focused leadership. In my 45 years of engineering experience, I have learned that technical solutions only succeed when supported by strong professional advocacy. When it was expanding computer network and computer adoption as a president for IT Association for 3 years, 3 terms, 6 years, or solar implementation in Maharashtra. I have myself, as Dr. Khedkar has pointed out, I have myself filed 5 PILs with MERC under for public interest. I have filed the net metering petition, case 86 of 2013. You can go to MERC website and check. And we could get net metering in Maharashtra. And now you have witnessed in last 10 years, 8 to 10 years, the entire power scenario in Maharashtra has totally changed. So that was a pivotal point where the net metering was introduced, where whether it is IT, whether it is solar, or whether it is energy management, the pattern remains same. Our profession needs leaders who understand both technical details and broader organizational dynamics that require lasting changes. As I conclude my session today, I want to leave you with one question. How can we ensure that technical excellence of each of our members translates into the kind of industry leadership that our profession deserves today? The answer lies in having representatives who have both technical excellence and managerial, the regulatory advocacies. And with this, I would like to conclude. Thank you very much. If you have any questions, I think you can unmute yourself and see. Is there any query? Okay, then on behalf of, I think there is one question. Good evening, everyone. Sanjeev Jain from Indore. Okay. Uh, if there is any question, I can take it up, or we can conclude this session. Okay, on behalf of Dr. Khedkar, I will like to thank all of you for attending this today's session, and let's meet again in the monthly programs that Dr. Khedkar has already planned for same.